This is fluid coding and AI. Z.ai says GLM 5.3 has the same base model as 5.2, yet its coding scores jump. That makes this more interesting than a normal upgrade. It gives us a rare question: how much can post-training alone change an agent once the repository gets messy? Start with the strongest public receipt. On Datacurve's DeepSWE version 1.1 board, updated August 20th, GLM 5.3 Max is listed at 69% plus or minus 3. 5.2 Max is at 44% plus or minus 2. Average cost is almost flat, $3.99 versus $3.92. Same mini-SWE agent harness, 25 displayed points apart. Impressive. Also very specifically bounded. Z.ai says both releases use the same base model and credits the improvement to another month of post-training with more environments, more varied tasks, and more compute. Think of the base as the engine and post-training as driving school. The engine can stay the same while the driver gets much better at navigating traffic, using tools, and finishing the trip. But that lineage is a provider claim. 5.3's official weights were not available in the source review, so it has not been independently verified from checkpoint metadata. Even if the claim is exactly right, same base does not mean everything else is controlled. The final post-trained weights differ by definition. Serving, hidden routing, sampling, reasoning effort, context policy, system prompts, edit tools, retries, and verification can all move the result. DeepSWE controls a valuable slice of that problem with immutable repository commits, short prompts, handwritten behavioral checks, and one shared bash-only agent. But it still measures one suite, one harness, and one verifier regime. It does not automatically predict your repository. Now the part that changed my expectation. The clean benchmark is not the hardest transfer test. A malformed test result is: give both agents the same tool response containing truncated JSON or an exit status that contradicts the body. Does the model inspect the bad receipt, retry, and find another check? Or does it confidently announce that the build passed? That single perturbation can expose whether better benchmark performance became better engineering judgment or merely better performance when every tool behaves politely. To answer that, the primary lane must use the raw API through the same endpoint. Freeze the repository commit, container image, harness commit, dependency lock file, system prompt, user prompt, tool schemas, sampling settings, context cap, retry policy, and verifier. Use byte-identical inputs wherever the model identifier must not differ. Record request IDs, errors, token use, cost, and every visible tool action. If a provider failure occurs, report it as a provider failure, not a model mistake and not a convenient deletion. Thinking policy needs its own lock. 5.3 requires thinking to be enabled and supports low, high, and max effort. A request copied from a 5.2 integration with thinking disabled can fail before inference. That is a useful migration tripwire, but it is not a coding result. For the real comparison, pair high with high and max with max, use the same preserved thinking policy, and return historical thinking blocks exactly as the API expects. Otherwise, the test quietly changes the memory system between contenders. Matched labels are only the first pass. Max versus max does not prove equal hidden compute. So run a second view with hard ceilings on output tokens and tool steps. Repeat every task, ideally 5 times and at least 3, because one heroic demo is just a demo wearing a lab coat. If no seed is exposed, preserve every request ID. Report both scheduled trials and valid completed trials so timeouts and API errors cannot disappear into the denominator. The first repository condition is a normal Brownfield change, multiple files, hidden feature checks, regression checks, and a clean verifier container. Then add ambiguity. Put the correct local convention beside a tempting legacy pattern and require one non-obvious integration point. Failure is not merely a red test. It includes duplicating an abstraction, rewriting architecture without need, editing unrelated files, stopping before verification, or leaving the required patch uncommitted. Accepted delivery is stricter than code that looks plausible in a chat window. After the first patch, Inject the same frozen reviewer note into both runs. It should identify one false assumption and one missing acceptance criterion. The test is not whether the agent enjoys feedback. The test is whether its next patch absorbs the correction without arguing past the evidence or bulldozing unrelated code. Strong agents still get corrected. What matters is correction uptake, edit locality, and whether the verifier moves from failure to a genuinely accepted patch. Then compact the context at the same recorded threshold. Do not let each model summarize itself and call the difference memory. Replace both histories with the same deterministic state packet, constraints, file paths, completed checks, accepted decisions, and the one open failure. Now measure whether each agent preserves the contract, avoids redoing finish work, and remembers verifier state. A natural Z-code compact run may also be useful, but it answers a different question about the product stack. The primary score should be accepted delivery rate. Hidden feature checks and regressions all pass on the committed patch inside a clean container. Then, keep the details that leaderboards compress away. Count malformed result recovery, correction uptake, retained constraints after compaction, tool steps, repeated commands, unwanted edits, total cost, and human cleanup. Publish hashes for prompts, commits, schemas, verifier files, reviewer messages, and compaction packets. Private reasoning stays private. Diffs, tests, traces, and aggregate usage provide the audit trail. Keep Z-code and coding plan in a separate lane. Goal mode can preserve objectives and verification state, continue after failures, and recover sessions. Z-code also provides compaction, while coding plan uses a dedicated endpoint and preserved thinking by default. Those conveniences may produce a better paid workflow. They just cannot be credited entirely to raw GLM 5.3. Measure raw model behavior first, then measure the complete product stack as its own system. Both results matter, but they answer different buying decisions. So the current verdict is deliberately narrow. The public evidence supports taking GLM 5.3 seriously on one common DeepSWE setup. The display gain is large and average cost is nearly unchanged. It does not yet prove the gain survives your brownfield code, corrupted feedback, reviewer correction, or compacted context. Until frozen local runs produce patches and verifier reports, there is no honest channel run winner to announce. The adoption rule is simple. Choose the system that lowers cost per accepted patch and reviewer cleanup on your repositories, not the one with the prettiest isolated percentage. If this kind of controlled AI coding analysis helps you separate model gains from product magic, like the video and subscribe to Fluid Coding and AI.